All right, good morning. We are going to start off our 104 class by actually looking at page 20. So on page 20, we had example 16 that I wanted you to take home with you from yesterday's class. And I wanted you to just kind of organize your thoughts in terms of what techniques you use for which specific types of expressions versus equations. So I want to start there just to make sure that we're all on the exact same page before we actually finish Unit 2 notes today. I anticipate that once we are finished with Unit 2 notes, I can take any, mini questions you may have, and then we'll move right into Unit 3. So that's the plan for this first session today. At 12:30, I'm going to live stream my next class, our Thursday class, and that will definitely be on Unit 3. Unit 3 covers exponents and radicals. So we're going to start off pretty tame because it's essentially a review of everything that you already know and have seen a few times thus far. And then I'm hopeful to have our second live stream for the day at around 4. I'm anticipating 4 or 4:30. So you can be on the lookout if you'd like to attend the live stream. So 2 more sessions later today. Join me if you can. All right, perfect. So let's take a look at page 20 before we continue with our word problems from yesterday. So our first expression essentially shows that all we're doing is adding fractions, right? So generally speaking, when we think of adding fractions, I want you to think of LCD, right? When we add fractions, we most definitely need an LCD. The only issue here is that our denominator, 2x minus 6, can actually be factored. So I want you to look at this as 4 over x plus 3. That's a minus. Yeah. Hello. Good morning to me. Great way to start the day. Okay. So x minus 3. Then we have plus, and we have 5 over, and I'm just going to factor the denominator. So it's 2 times x minus 3. And then we have plus 1/2. Now, my common denominator is essentially the combination of my factors, right? So we have a factor of x minus 3, we have a factor of 2, and then we have the combined factors. So my LCD is simply 2 times x minus 3. We don't need an extra 2 here, and we don't need an extra x minus 3 because it's already here. When we think about introducing what's missing, I like to say to myself, well, I have the x minus 3, but what I'm missing is the 2. So I have to introduce a product of that factor of 2. So my second fraction is fine. My third fraction, it's missing that x minus 3 piece. So I'm going to introduce the x minus 3 to both the numerator and denominator. First off, if we thought about restrictions, notice the denominator, we have x minus 3. If we were actually solving it, we would say that x can't be equal to 3. But luckily for us, we're not actually solving. We don't have any worries of, oh no, am I going to get a 0 in the denominator? No, that's not going to happen at all. We're just adding or subtracting fractions. So now I'm going to actually multiply those numerators, like for instance, 2 times 4, and then over here, 1 times x minus 3. And I'm going to write the combined numerator over the common denominator. So that leaves me with, we have 8 plus 5 plus, and then 1 times x minus 3 is just x minus 3. And this entire numerator is over your common denominator, which is 2 times x minus 3. I feel like using that language is helpful too, because you're like common denominator. So you don't have to rewrite it again and again and again. So then we have 8 plus 5, which is 13. 13 minus 3, which is 10. So we have 10 plus x over 2 times x minus 3. If we could factor, we would. But this 10 plus x or x plus 10, they belong together, and you can't factor any quantity out. so we're actually done with this particular expression. Okay, for our simplified expression, I might just write it in descending order in the numerator. So x plus 10 all over 2 times x minus 3. Remember, you can only cancel out common factors, not terms. Some of you may have been tempted to say, oh, 2 goes into 10. But you can't do that because the 10 is attached to x by addition. So it's 10 plus x, and 2 can't go into those. All right, for part B, we have a couple different techniques. This is a complex fraction. I personally like the technique where you multiply every fraction in the problem by the same LCD so that you can cancel fractions. I really like that. I feel like it helps, you know, us to move through the problem rather quickly. So in this case, it's actually going to be really nice as well. So first, let me rewrite this. So we have 4 over x minus 3 all over. And then we have 5 over 2 times x minus 3. Remember, you always want to factor your denominators, and then plus a half. So we are going to, same idea, LCD, right? We know the LCD is 2 times x minus 3. So because I want to clear fractions, I'm going to multiply every single fraction by the LCD, like this. Put every term in parentheses, 2 times x minus 3, 2 times x minus 3, 2 times x minus 3. Okay, that goes everywhere. And then the really cool thing is we can start to cancel out fractions. So the x minus 3's go away, and you're left with 4 times 2, which is 8, over. The 2's cancel. The x minus 3's canceled, so that leaves us with a 5. Plus, the 2's cancel, and we're left with 1 times x minus 3, which is x minus 3. The next thing we want to do is we want to simplify the denominator. So we have x, and then 5 minus 3 is 2. So our restrictions stay the same. If we were solving, our x cannot be 3. Luckily, we're not solving at all. We're just simplifying the expression. And then I want to comment that you don't have to use just this technique. I just like it a lot. And I hope that you have been finding it to be very useful. In our denominator, we have the binomial x plus 2. So keep in mind, we cannot just reduce terms. This is not allowed. So our answer is 8 over x plus 2, and we're done. For the last problem, 4 over x minus 3 plus 5 over 2x minus 6 equals 1/2. We definitely want to know our restrictions. This would be the case where we would definitely say, okay, x can't be 3. We want to make sure that doesn't happen. We rewrite the problem. We're still going to use the LCD. Notice that we use the LCD in every single case, which is nice because it's consistent, right? It lends itself to that idea of, okay, I don't have to like really overthink this because the process seems very similar. In this case, notice with our first problem, our first example, we did not cancel fractions. So for this problem, you can't cancel fractions. That's not why we use the LCD in this case. Keep that in mind. With our first example, that's not why we use the LCD. We use the LCD so we can add or subtract fractions, which means we have to keep the denominator. If I could have simplified at the very end, then I would. But in this case, you couldn't, so you needed to make sure that your denominator was still there. However, for parts B and C, the use of LCD is to cancel fractions. That's one style, right? Use LCD to cancel fractions. You don't have to use this style, but I chose to because it lends itself really nicely. With part C, that's the exact same idea. you're going to use the LCD to cancel fractions. That's the difference. I think it's really important to note so that as you're moving through these problems on your own, you won't be caught off guard and you won't say, you know, oh shoot, what do I do here? Okay, we're going to multiply every term by 2 times x minus 3 so that we can cancel fractions, just like I mentioned before. So the process is essentially the same. We have 8 plus, and notice both of these factors cancel. 5 is equal to, notice the 2's cancel. 1 times x minus 3 is x minus 3. You are going to combine like terms. So we have 13 is equal to x minus 3. Let's add 3 to both sides. And we find that 16 is equal to x. So your solution set in this case, notice you actually have a set, right? Because you had a solution. So we're going to write 16 in braces, and that's the final answer. Any questions on this page with differentiating between the 3 types of problems? All right, beautiful, beautiful, beautiful. This takes a little bit of practice. Make sure you're doing that, okay? I like these a lot. Hopefully you're finding problems like this to be super straightforward. Cool. Let's pick up where we left off, which was example 20 on page 22. We filled in the chart completely. And I also highlighted the fact that it is saying that a car travels 250 kilometers in the same time that a truck travels 225 kilometers. So because the times are the same, essentially our equation becomes the time that the car traveled is equal to the time that the truck traveled, right? That's essentially our equation here. So we're going to replace the time from our chart into the equation itself. So we should have 250 over 8 plus t is equal to 225 over t. Now, I want to show you an alternative to what we did in our previous problem. I'm going to scroll up for a moment. Notice in our previous problem, we used the LCD. So the LCD was b plus 6 times b minus 6. We multiplied both sides by that expression, and then we canceled out common factors. I want to show you that that is the exact same thing as cross multiplying. The only reason we're allowed to cross multiply is because this is actually a proportion. This is a proportion. That's the only reason it allows us to cross multiply. You don't have to use this technique. If you wanted to multiply both sides by t times 8 plus t, because that's your LCD, then go for it. That'll totally work. But because we have a fraction equal to a fraction, sometimes I like just cross multiplying, right? Because that's an option that we have here. So 250 times t is 250t. Then we have 8 plus t times 225. And I'm just going to rewrite it first before we actually distribute to solve. So make sure you have your calculators handy. So we have 250t is equal to, so let's distribute that 225. That gives us 1800 plus 225t. Remember, your goal is to solve for the variable. So it only makes sense to subtract that 225t from both sides. Beautiful. That goes away. 250t minus 225t is 25t. That's equal to 1800. And then let's divide both sides by 25. We get that t is equal to 72. Okay, so now I have a question. What does that t equals 72 represent? Who can tell me what that even means?
Is that the time?
I mean,
it's the speed of the truck.
Yes, it's the speed of the truck. Now we could take this 72 and plug it into the denominators in each of these fractions 4 times. So yes, I absolutely can. but we had to be careful. We use T for truck. And when we go back to the chart itself, check it out. T by itself represents the rate or the speed of the truck, which means that that truck goes 72 kilometers per hour. So I'm going to start by writing my answer. The truck's speed is 72 kilometers per hour. Very nice. What about the car? So not Shane, someone else. What about the car? How fast is the car going?
80.
Yes, the car's speed is, and notice we have T, which is 72. According to our chart, the rate of the car is 8 plus whatever the truck was going. So it's going to be 8 plus 72, which is 80. So we're going to say 80 kilometers per hour. And that's your final answer. What are your questions for me on number 20? Okay. If you don't have any questions on this, this must mean that these two problems went really well, which also means that you in your groups can complete problem number 21. So I'm going to go ahead and put you into breakout rooms so we can just kind of, have a little bit more energy. We're talking to each other, checking in, all that good stuff. And I'm not going to set a time limit. So I'm going to just hop around room to room and make sure everyone's doing okay. So let's do 3 to 4 participants per room. And I'm going to open this up and good luck. Okay, sorry to pull you back from the breakout rooms, but I wanted to make sure that we were all on the same page and we were dissecting this correctly. So when I visited the breakout rooms, I found that you all had similar ideas, which was fantastic. And that is, we're told that Ben can bike 4 miles per hour faster than Lana. First off, that means rate is miles per hour. My time is in terms of hours and distance is in terms of miles. Sometimes it's helpful to make note of what those units are. So Ben bikes 4 miles per hour faster than Lana. I'm just going to use an L to represent the speed in which Lana was riding her bike. We're then told Ben leaves half an hour after Lana. This is interesting because it pertains to time. And we will figure out what we do with that in just a second. So we're not going to touch that yet. When Lana has ridden 35 miles, Ben has ridden 30 miles. So we're able to fill in that much of the chart. Additionally, we know that time is represented by distance over rate. So if we think about Ben, we'll say his distance is 30 and his rate is 4 plus L. When we think of Lana, her distance is 35 and her rate is L. Now, just like our previous problems, we wanted their time to be equal, right? So I'm going to write something down. So time for Ben equal to time for Lana. Except what I just wrote here is a flat out lie. That's not true. You know it's not. You're told that Ben leaves a half hour after Lana, right? Which means Lana was traveling a half hour longer. If we want them to be equal, we have to give Ben the half hour. If we want them to be the same, we want to give Ben the half hour. I'm going to write in words what I just said. Lana was traveling a half hour longer than Ben. That's what that statement says. If Ben leaves a half hour after her, that means that Lana was traveling for a half hour longer. So in order to make them equivalent, we want to give half an hour to Ben so that this statement is now true. All right. We want their time to be equal. I'm going to make another note. We want their times to be equal. Okay. And that's why we add a half hour to Ben. So let's fill everything in. We have 1/2 plus, we know that Ben is 30 over, if it's okay with you, I'm just going to switch the order. Instead of 4 plus L, I'm just going to write L plus 4. And that's equal to Lana's time, which is 35 over L. As you do these kinds of problems, it's going to help out if you write in words what your equation is. This way it makes sense prior to actually plugging values in. I would rather you write it in words so that it serves as a guide than just being like, oh, okay, let me just write some numbers in there. Because we have an equation with different denominators, we want to use the LCD to cancel fractions. Our LCD in this case is going to be a combination of all 3 denominators. We have a 2, we have an L, and we have an L plus 4. Remember that L plus 4 is a package deal. You can't just take parts of it away. So when we find the LCD, we need all 3 denominators. I am then going to multiply every term by the LCD, which is 2L, L plus 4, 2L, L plus 4, 2L, L plus 4, and now I'm going to go to town canceling. So the 2's cancel. I'm left with L times L plus 4 plus, notice the L plus 4's cancel. So I'm left with 30 times 2L, which is just 60L. And then my L's cancel, just the ones that are by themselves, okay? Not the one inside the parentheses. And that leaves me with 35 times 2 times L plus 4. Well, I know 35 times 2 is 70, and we still have that L plus 4. Okay, all we did is we went through and we canceled out common factors. Are there any questions at this point? Okay, so our next step is going to be what? Where do we go from here? Shout it out.
Combine like terms.
Multiply.
Multiply. So we're going to distribute first, and then we're definitely going to combine like terms. So L squared plus 4L plus 60L is equal to 70L plus 280. We're definitely going to combine like terms. So we have L squared plus 4L and 60L is 64L is equal to 70L plus 280. What's next?
Bring the 70 over.
Yes, we're going to bring this 70 over. So we have L squared minus 6L is equal to 280. What's our next move?
Plus,
L.
yeah, no.
Oh no, I'm sorry. Make it equal to 0. Bring the 280 over.
Yes, there we go. Set equal to 0. I'm going to make a note here. We're going to set this equal to 0 so that I can do what? What technique?
Factor.
Yes, beautiful.
It's your dog right there, Professor.
What's that?
Your dog right there.
Yes, you can hear her snoring.
Yes.
Oh my gosh. If it's too distracting, let me know.
No. Don't.
She's really, really cute. She had her tongue out earlier. It was so freaking cute. She was sitting up, eyes closed, tongue out. Okay, so we are going to factor this. Let's go ahead and write our sets of parentheses. I need factors of negative 280 that combine to give you a negative 6. So our goal is a -6. 28 and 10 won't work. Let's look at some factors. Oh, I found it. We could do 20 and 14. So 20 times 14 gives us 280. We want a -6, so we want the 20 to be negative. So -20 times 14 is -280, -20 plus 14 is -6. Now let's throw it inside the parentheses. So we have L minus 20 and then L plus 14. When we go ahead and solve, what are my two solutions here? L is equal to
20,
and
-14.
perfect, which means
The 20 is the answer.
yes. And what does this represent?
It's Lana's speed.
Yes, perfect, Lana's speed. Take a look. I'm just gonna move this up for a second. I apologize if I'm moving this too quickly. If we go back to our chart, notice L by its lonesome here, that represents the rate in which Lana rode her bike. And all we're looking for is Lana's speed. If we wanted Ben, that's no big deal. We know Lana's speed is 20, so Ben's going 24 miles per hour, but we just want Lana. So we're gonna say that this means Lana, or Lana's speed, is 20 miles per hour. That's how fast she's riding on the bike. As a reminder, Lana cannot go -14 miles per hour. That's just weird. So we're going to cancel that out because that's an extraneous solution. Excellent work. Excellent work. These motion problems tend to be, just a tiny bit tricky. I'm hopeful that because they all followed the same kind of format, like looking at your times were either the same or they were slightly different. We had to account for that. That they essentially had the same feel, and you were able to move through that with pretty decent ease. I know that it's going to take a little bit of practice, so don't worry about that. Just continue to, maybe either even try these problems again or check out the homework in Lumen so that you can make sure you're understanding it. Okay. As always, if you have any questions at any point, don't hesitate to ask me. All right. The last section of Unit 2 revolves around work problems. There's a lot of language right there at the very start of this page that talks about like the rate of work, right? So I want to paint a picture for you, almost quite literally. So I want you to visualize that somebody hires you to paint a room. Okay, can everyone think of that? You are currently being hired to paint a room. If it takes you, for instance, let's say I wanted you to paint this room. If it would take you 5 hours to paint this room, how much of the room can you paint in 1 hour? And hold that thought. Don't say anything yet. I just want to type what I said in the chat. And I would like everyone to read this. It takes you 5 hours to paint this room. How much of the room can you paint in 1 hour? I want you to just think about that for a moment. Logically speaking, how much of the room can you paint in 1 hour, according to how long it takes you to paint the whole room?
A wall.
A wall. What's that?
A fifth.
A fifth. That is correct. So in 1 hour, you can paint a fifth of the room, right? Because if it takes you 5 hours to paint the room, then your work is a fifth per hour, a fifth of the room per hour. If it takes you 7 hours to paint the room, then you would do a seventh of the room in 1 hour. Is that making sense, like that connection? That's essentially the setup for work problems. So we think about every person's contribution to the task at hand, right? So for instance, if I am partnering with any one of you to paint this room, we know it's going to be faster, but we each have our own rates. Let's say it would take me just 3 hours. I could do a third of the room in 1 hour. If it takes someone 5 hours, they can do a fifth of the room in 1 hour. But combined, we are collecting our work speeds essentially to complete one task. So what I'm actually going to do is I'm going to provide to you a formula that I like a heck of a lot more than any of the other stuff that I've seen before. And I'm going to write it in your notes. It's going to seem a little bit weird, but it's actually really, really nice. Check it out. So notice here you have a formula, part of task done by one person or machine, part of task by another, blah, 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 and then equals one completed task. By the way, you see that we have a plus sign here. This is if two machines or people are actually working together. Imagine that, you know, you're cleaning up a room, but you have a little kid and they keep throwing toys back in. So you're trying to throw the toys out and this little kid is throwing toys back in. That means you would be a subtraction property here. We're subtracting the work because obviously someone's trying to sabotage you, but it's not going to be fast enough to prevent you from getting it done. So anyways, just a little side note. The formula I would like you to use is as follows. Together over alone number one plus, now remember that sign is going to change if something's working against you. It'll be minus if something's working against you. Then we have together over alone number two, and that's equal to one completed task. Okay, together over alone plus together over alone equals one. When I say together, I mean the time it takes when your characters actually work together. Let me show you what I mean. Okay, Ben and Rebecca have to mow the lawn. Working alone, hint, hint, it would take Rebecca 2 hours to mow the lawn. It would take Ben 3 hours. How long will it take them working together? Okay, is it clear that in our formula, together over alone, I'm just going to write it again. And I want you to do this because I want you to essentially commit this to memory. We are told that Rebecca takes 2 hours alone to mow the lawn. So the denominator is 2. And obviously this first fraction refers to Rebecca. We are told that it would take Ben 3 hours. So that's his alone time. We have no idea how long it would take them working together. So I'm just going to call the numerator W. And that's essentially what we're solving for. Okay. How would I solve this equation? Jose, what do I need in order to solve this equation?
LCD.
Yeah, what is my LCD?
2 times 3, I think.
Yes. So in which case our LCD is simply 6. So let's multiply every term by 6, which is my LCD. I'm going to make a note. My LCD is 6. We know that 2 goes into 6 3 times. We know that 3 goes into 6 twice. So we have 3W plus 2W is equal to 6. 5W is equal to 6. Divide by 5. And then we see that the time it takes for them to work together is 1.2 or 6/5 hours. I like seeing time in terms of decimals just so that you can get an idea of what's happening when we figure out how long it takes. So working together, they're clearly moving faster than the fastest person because there's an additional hand. All right. Good. That's it. That's all really that there is when you look at work problems. Not bad, right? So let's write, it will take them 1.2 hours working together. Perfect. and you're done. Turn the page when you're ready.
And these are rookie numbers.
What's that?
These are rookie numbers for 23.
Yes.
It takes me at least an hour.
Oh, damn. They must not be doing a good job. No, I'm just kidding. Juliet and Alexandra have to wash their car. Working together, it would take them 18 minutes to wash the car. Working alone, it would take Alexandra 30 minutes. How long would it take Juliet to wash the car alone? I want to volunteer. Who can tell me the equation for this?
So it would be 18.
Wait, hold that thought. Can I write the equation real fast? Together over loan number 1 plus together over loan number 2. We know it's plus because they're working together. Okay, sorry. Go for it.
So it would be, let's go with the variable. So it would be 18 over, I'm gonna say J, Juliet,
Cool.
plus 18 over 30 equals 1.
Yes, that's exactly correct. You know that it took Alexandra 30 minutes, so we'll put her part here. Juliet is the one that's unknown. Thank you so much for using J for Juliet. It's going to be so obvious when we solve that that's the answer. Very nice, Shane. Phil, in this case, what's your LCD?
Would be 30J.
Yeah, beautiful. Let's multiply every term by 30J. Perfect. And we just go through the process of solving this. The J's cancel. Let's use our calculators if we need. I'm not a human calculator. So 30 times 18, that's our 540. Notice that 30s go away. So J times 18 is 18J. And then 1 times 30J, that's just 30J. Cool. And then we're going to continue to solve this. Let's subtract 18J from both sides. You can follow along and just make sure that you're getting the exact same answer that I am getting. And I find that J is 45. Super cool. What does this 45 represent? So not Shane, not Jose, and not Phil. Anyone else? What does the J equals 45 represent?
The time it takes to wash a car.
Yes, who?
Juliet.
Perfect. So Juliet takes 45 minutes to wash the car alone. Cool. Very nice. Take a look at this next one. If I'm moving too fast, please tell me. When the water is turned on and passes through a small hose, a pool can be filled in 6 hours. That's the small hose. When the water is turned on at 2 spigots and passes through both the small hose and the large hose, the pool can be filled in 2 hours. How long would it take to fill the pool using only the large hose? Okay, I would like you to try this on your own and send me your answers privately in the chat to a few minutes. Okay, so we still want the exact same formula. This is why it's so important and helpful for us to write this down. So we want together over a loan number 1, however long it takes that individual, that character, whatever, to do the work by him or herself or their self. Plus, we're adding this because essentially we know that the two hoses are working together. So we have together over alone number 2. And the nice thing about these equations is that they're completing one whole task. So it's always going to be equal to 1. You are told that a small hose can fill a pool in 6 hours. This is implying that the small hose alone can fill that pool in 6 hours. So we'll have the first denominator be 6. Then when the water is turned on at 2 spigots and passes through both the small and the large, both, that's the key word, then it can be filled in 2 hours. So what that implies is that if both hoses are working together, that's the together part, that it takes 2 hours. So we're literally replacing together with 2 in both fractions. Your second denominator refers to how long it takes the large hose working by itself. So I'm just going to write H here. We have no idea how long that's going to take, but that is our setup. So we should have 2 over 6 plus 2 over H is equal to 1. Christina, does that help when we break it down like this, like the together over the alone, together over the alone? So meaning the togethers will always be in the numerator, and then the alones will always be in your denominator, okay?
Yes, that does help.
Sweet. So once our setup is completed, we can now just use our LCD. So we know that our LCD is 6H. We're going to multiply every term by 6H here. Notice your 6's are going to cancel. So 2 times H is 2H plus. Your H's are going to cancel. 6 times 2 is 12. And then 1 times 6H is 6H. All we have to do is solve. Let's bring over the 2H. We get that 12 is equal to 4H. And then, of course, divide by 4. We find that H is equal to 3. So the large hose takes 3 hours to fill the pool alone. And that's your answer. I don't want you to overthink this or overcomplicate it. You have a formula. Make sure that you're applying that formula to your problem, okay? If you turn the page, we have one last problem for unit 2, and that is negative work, meaning one pump is filling, the other pump is taking it away. So I want you to take this one home as well. So take home, or you can do this on our break, which we're going to take right now. Okay, so let's take a 5-minute break. I do want to let you know that I will complete this page. I'm going to scan your unit 2 notes and I'm going to put them into Lumen. When we come back in 5 minutes, we're going to start unit 3, unless you have some questions you'd like to answer first. Okay, so we will start unit 3 as soon as we return. So how about we come back at 10:13? Okay, I will see you all back at 10:13.
Professor, can I just see that last page real quick?
Yeah, of course.